Got to turn my microphone back on. Oops. Oh well. Shit happens. Can't do anything about it now. I even, when I walked out, I almost reminded you, I was going to remind you to tell me to turn it back on. Okay, it's on now. First quadrant, and then I have to be inside a circle of radius square root of 3. So here's root 3. Here's root 3. Everything in there, including the boundaries. Right? So we start by first looking at the partial, setting them equal to 0. So what's the partial of f with respect to x set equal to 0? That's y squared is 0. Next, partial with respect to y equal to 0, which is 2xy must be 0. Well, this already tells me that what? Y has to be 0 in order for that to be true. And over here, shit, what does this mean? How do I make this one true? This says y has to be 0, right? So over here, does x have to be 0 for this to be true? No? Why not? Because if y is 0, then it doesn't matter what x is, does it? If y has to be 0 to make that true, then y has to be 0 here, and then you can let x be whatever you want it to be, right? So we actually have x is free. Call it free variable. It's free to be whatever it wants to be. So we have an infinite number of points that satisfy this, don't we? They all look like this. They all look like that. Do you agree? Any point that looks like this will satisfy these two equations. Thank goodness, though, these points coincide with what? This is your x-axis, isn't it? That's what this is. This is your x-axis. And it turns out that that's the boundary of one of my sides. So we got lucky that the only critical numbers or critical points we're going to get from this right here is actually what we're going to be looking at in just a second. So what if we didn't? What if we didn't have that? What if that was somewhere inside here? Well, then we would have to plug these into that and figure out what happens. It would be almost the same exact story. We plug those in, figure out what that is, and then take the derivative. Okay, so let's move along these. L1, I'll call this L1, will be along this edge. L2 here. I shouldn't call that L3, right? It's not straight. So I'll call it C1 for curve 1. So I'm going to go around L1, L2, and C1. I think we can move quicker through this one. On L1, tell me what the points look like. X0, what's my restriction on x? 0 to root 3. Okay, plug in x0 into the function. Oh, come on. 0. Which means I can stop. It means that if you plug any point in along this edge, the function spits out 0. Right? That's what that means. I don't need to keep on doing any work, right? Take the derivative of 0. Go ahead. I mean, right? I mean, there's no need to do this. We're done. That was nice. L2? What do all the points on L2 look like? 0y. What's my restriction on y? 0 to root 3. And what's f of 0y look like? 0 again. Same exact story. It could potentially be that 0 is my minimum. It could be potentially that my 0 is my maximum. I'll have to check in a second. Now let's move along C1. So C1's the harder part. So along C1, what do my points look like? Dun, dun, dun.
Is it 1, 4,
Okay, so if I come in here and I pick some arbitrary value right there, and I call that x, then how far up am I going to move? So if I call this x, then what's my y coordinate going to be?
x cubed?
Yeah, you could basically take this as an equation, solve it for x.
The point wouldn't, well, for that line, wouldn't it be sine t, cosine t, but restricted?
Yeah, but that's if we, yes, we could do that. But now what you're doing is you're reparametizing the curve. We would like to have everything in terms of x because of the derivative we're going to take in a second. So you're turning it into a vector function, which you could still do. But I think it's too much work for us. We don't need it that much. Square root of 3 minus x squared. So, well, you tell me. What coordinate is this? It's the y coordinate, right? So what you're doing is you're trying to solve for the y. So you solve for y here. You move x squared over. You take the square root. I'm only looking at the positive root. Why? I'm on the top half, right? I'm on the top half. Understand? Yes? Now, what's my restriction on x? 0 root 3. So I have to pick an x that comes from between here and here. All right, now I get the pleasure of plugging that in. So I'm going to plug that into the function. What's f of x root? Ooh, I'm going to get lucky. That is x times y squared. Square that. Oh, nice. That got rid of the root for me, didn't it? Happy. I'm happy. And this is just 3x minus x cubed. Agreed? Now let's find the critical numbers of this. We've never had a cubic, right? We've had a line. We've had a constant. Like along this one, it was constant. We've had a parabola. We've never had a cubic. Well, anything can come out of these. It just depends on your boundary. It depends on your function. You just now need to be able to take derivative of this. So derivative of f of x root 3 minus x squared is 3 minus 3x squared. And now you're going to set that equal to 0, right? So set equal to 0. And you get x is what? 1 and negative 1? Right? Plus or minus, but why not negative 1? So you get x plus or minus 1, but because x equals negative 1 does not live inside of, where is it, here, we throw it out. So, got it? So that means I need to look at a couple of things here. I need to look at, from here, f of, let's do the endpoints. I plug in 0, right, for x. I get 0, and then when I plug in 0 here, I get root 3. I need to look at f of, now let's plug in root 3. So that gives me root 3 what? 0. And then I need to look at the most interesting one, which is x is 1, which means that the y value is what? So just 1 in here, you get root 2. And figure out the values of the function at each of those. How about the first two? 0, right? If I plug in 0 for x, that's gone. Plug in 0 for y, that's gone. So we already knew that, didn't we? We already knew that along these two edges it's 0. So at the corners, or at the two ends of my arc of my circle there, I'm going to be 0. But at that point, 1 root 2, I plug it in and I get what? 2. So can we conclude now? Are we good? We done? Do you have enough information, you think, now? What's your maximum value? Maximum value is 2. Where does it happen? 1 root 2, 2, yeah? What's the minimum value? 0. Where does it occur? It's a little more interesting, right? How do you answer that? It answers. Anywhere where you have x 0, you're going to get 0, right? As long as x is between 0 and root 3. And anytime you have 0 for x, and who cares for y, and as long as your y is between 0 and root 3, that's where you're going to get your minimums. So we're saying that's just how we say along this edge and along this edge. Make sense? Shall we take a look at the picture? All right, let's take a look. Was that a question? No? Okay. There's your domain. There's a domain on the ground. Here's the surface. Weird looking thing. Here's the surface restricted. Okay. And there are the points that we found. Now, I actually did not include, I should include every point on this edge, right? Those are my minimums. Every point on this edge are my minimums. But you can see that part right there. There's our maximum right there. All right? Okay, last one for this section. I think that the page number on that might be wrong. Someone can check on that in a minute. But all right, so let's do a word problem. Find the largest rectangular box with edges parallel to the axes that can be inscribed in an ellipsoid in this ellipsoid. So look at it this way. You have an ellipsoid, right? Here it is. The orangish thing is the ellipsoid. And we want to put a box inside of it. And we want it to be inscribed. When we say inscribed, that means that this point, this point, this point, and this point touch the edge of touch the surface, right? And the bottom edges touch the surface inside. That's what it means to inscribe it. I want to find the largest volume possible. Does this look kind of like a Cal 1 problem? Maybe, maybe not. So look, if I go really tall, what happens? I get a very tall box, right? But it's very narrow. And look, the volume right now is 1.7. I'm having the computer calculate it for me. If I change, make my y value and my x value bigger, you can see I'm getting a bigger volume, right? 6 now. But if I go too far, see if I go too far, what happens is that you're getting more width, but it's shorter. So there's got to be some optimum solution, right? Some optimum. This is an optimization problem. But now we are armed with being able to treat this as a function of 2 variables instead of a function of 1. Okay? Understand geometrically what we're trying to do? Okay, here we go. What are we trying to find the maximum of? Volume, right? We want the maximum volume, which means that you now need to tell me what the equation of the volume would be then. If you're trying to maximize volume, you better be able to express that in terms of some variables. So I'll start you off. V equals. Okay, what is it? X times y times z. Let's go back to the picture for a minute. Now remember, we're in three-dimensional space, right? So I have a little thing here that might help us out. Whoa, I don't know if that helped out at all. Why did the other one go away? Okay, look at this point. Can you all see that black point? That's in the first octant, isn't it? That point has the coordinates. You start at the origin, you go out x, right? You go out y, you go up z. That has the coordinates x, y, z. So if you say the volume is x times y times z, it's going to give you the volume of that box. Is that what we're talking about? Is that the box we're talking about? I want one bigger. So I want this point right here to touch the edge of the ellipsoid, right? So what's missing from this? What else do I need? The other 7 octants, exactly. There's another rectangle you need, or another box you need in the second octant, another box you need in the third octant, in the fourth octant, fifth, sixth, seventh, and eighth, right? So I agree with you. X times y times z will give you the volume of that box. The volume of the whole thing is 8 of those. So the volume should be 8 x, y, z. Agreed? Understand? So that's why I pulled that in there. I took this out. Now, I think if I do that, you can see it. See that? That's just one of the 8 pieces.